Hello, and welcome back to Physics 123, Quantum Mechanics 1. We are still on the chapter wherein we are trying to formalize quantum mechanics. So, before we proceed with today's lesson, let's first review some of the concepts that we need for this lesson. So, in the previous chapters, we have discussed about Born's statistical interpretation of the wave function psi. So, stipulated that the absolute value of psi squared is basically just a probability density function. So this is a probability density function. So probability per unit measure. So it's one dimension. It's if the measure is length. So this is basically probability per unit length. So you will notice that, for instance, it can be seen in the wave functions of a particle trapped in an infinite square wave potential. You have a factor of square root of 2 over a, where, if you will recall, psi n is square root of 2 over a sine n pi x over a. So the sine part is dimensionless, but here square root of 2 over a has the unit of length. So basically the unit of this wave function, the standard unit of this is 1 over square root of meters, or 1 over meters to the 1/2, or meters to the power of negative 1/2. So if you square this, you will notice that 1 over square root of meter, you have 1 over meter. So basically the unit of this is 1 over meter. You multiply by dx, which has a unit of meter, so you will get a dimensionless quantity, which is a dimensionless unit, which is the unit for probability, because probability is basically just a number. So according to Born, the integral of psi squared dx is the probability that the position x of the particle is between a and b at a certain time t, since this wave function is just the wave function for position x. So in this lesson, we will try to generalize the statistical interpretation of the wave function. So we will now be dealing with wave functions which are no longer constrained to position. Okay, so this is now the generalized statistical interpretation. So if you measure an observable Q of a particle in the state psi as a function of x and t, then you are certain to get one of the eigenvalues of Q. In this case, since Q here is our in this case, if our wave function is for position, then Q here, our physical quantity, should be position. And if we try to measure the position, we are certain to get one of the eigenvalues of position. So in general, it's this one. So if you have a discrete spectrum, then Cn squared will represent the probability of getting a particular or determinate eigenvalue Qn. So we have discussed this in the first chapter, that Cn squared basically is just a probability if you have a discrete spectrum. So again, the summation of all Cn squared will get you 1. And to get Cn, again, Cn are the linear combination coefficients. If you will recall, we can actually write our wave function in position and time as summation of n Cn psi n, the time independent wave function, stationary states, e to negative I ent over h bar. And Cn's here are just your linear combination coefficients, and Cn's here actually represents your probability. Rather, probability in energy space. So to get Cn's in general, you multiply your eigenfunctions. In this case, the eigenfunctions are psi n's to the initial wave function psi. And to get the expectation value of any quantity q, which has a discrete spectra of eigenvalues, then it's just the eigenvalue multiplied by the probability for all eigenvalues. If you have a continuous spectrum, then the probability is now this one. It's now an integral. It's integral of the coefficients squared. And this will give you the probability of getting a value of z between a and b. So it's no longer determinate as compared to the discrete spectrum. You can determine exactly the probability of getting an eigenvalue qn. In the case of continuous, since the spectrum is continuous, you can only get the probability of getting a value within a certain range. In this case, the range is a to b. So again, this is just an analogy. Here you sum all of the probabilities. You also sum all the probabilities here. Instead of a summation, you have an integration. It's still equal to 1. And to get cn's, you still use this inner product, but you transform it to the integral form. So the ones in the bra, the eigenfunctions are conjugated, and this is your wave function, the true wave function. And to get the expectation value, instead of a summation of your probability times the eigenvalue, you get you sandwich it between your so absolute value of cn squared means cn conjugate cn. So basically conjugate times c, and that is your operator q inside here. So there's an analogy between the discrete and the continuous case for the eigenvalues. Okay, let's first discuss the position space wave function. So these are basically the eigenfunctions of position. We have discussed this in the previous lesson. That the eigenfunctions of position is the Dirac delta function. So if we now try to find the time-dependent coefficients of these eigenfunctions, so we use the Fourier strict formula where we have the inner product of the eigenfunctions and the wave function. In integral form, it's this one. But since we already know the eigenfunction of position as a Dirac delta function, then this will give us, again, if you see a Dirac delta in the integrand, then there's no need to integrate. It's just the value of the function at x is equal to y or at y is equal to x. So basically, the time-dependent coefficients of the eigenfunctions of the position space, position eigenfunctions, it's just your position space na wave function. So it's just a special case now. So if you want to get the probability of getting a value of x between a and b, then you need to integrate your time-dependent coefficients squared dx. So it's basically just psi star psi, or absolute value of psi squared dx. And this is our original statistical interpretation, the Born's statistical interpretation of the wave function. So that's just specific for the position space wave function. Let's now go to the momentum space wave function. So in the previous lesson, we have determined the eigenfunctions of momentum. So this is just the normalization constant, 1 over square root of 2 pi h bar, and it's e to the ipx. To solve for the time-dependent coefficients, so we again use this formula that we have here. Now, this integral is just looks like a Fourier transform, and it's just a Fourier transform of a quantity which is now a function of momentum instead of time, because you are now differentiating here with respect to x, so there will no longer be an x, and what's left will be p and t. So the answer of this integral is a function of p and t, and it's basically a Fourier transform equation. So meaning you can actually get the momentum space wave function if you know the position space wave function, and vice versa. So we have actually encountered these two equations here when we discuss about the free particle. So if you want to get the probability that you will have a value of P, which is between A and B, then you get the general formula here. So similarly, it's just the absolute value of, in this case, it's now phi squared dp instead of dx. Okay. Let's go to energy space. So this is the position wave function. This is the momentum space wave function. And if you will notice, the position space wave function and the position and the momentum space wave functions are can actually relate this from this equation here, and vice versa. Now, if you see our equation here, where this is the position space wave function, can be written as a linear combination of the stationary states. If you look at the analogy here, you will notice that it similarly looks like this one, but this is just an integral. And in this case, your psi n is e to the ipx and then 1 over square root of 2 pi h bar. That gives the role of your psi n. And the role of your cn's here is this one, your momentum space wave function. So basically, this corresponds to the role of your c, and the term e to the ipx, that term here is your psi. So you have cn, psi n, instead of an integral, you have a summation. And the time component is actually inside here, c. So basically, this is your c of t, rather, no? C as a function of t. Okay, so from that analogy, we can actually conclude that the time-dependent coefficient in energy space based on this equation is actually this one, cn e to the negative I ent over h bar. So meaning, this original equation that we kept on using before is actually a transformation from the position space wave function to the energy space wave function, in a similar manner that this equation is a transformation from the position space wave function to the momentum space wave function. So we can actually say that this is now the energy space wave function. It's a function of Cn. And if you want to get the probability, since the spectrum, the energy spectrum is discrete, for discrete energy spectrum, so absolute value squared of this, our energy space wave function, so conjugate times itself, so the I, e to the negative I part will cancel each other out, and we'll just get this familiar probability that the energy is En. So essentially, we have now generalized the statistical interpretation of the wave function. Okay, let's have an example. So for a particle trapped in a delta function well, find the probability that a measurement of momentum would yield a value greater than this value here, p naught, is equal to m alpha over h bar. So alpha here again is just the strength of the delta function well. It basically tells you how fast or how deep essentially is the well. Okay, so for a particle trapped in a delta function well, there's only one bound state. So its state is given by this one, square root of m alpha over h bar e to the negative m alpha absolute value of x over h bar squared. So that is the bound state. There's only a single bound state, and there's only a single bound state energy. It's negative m alpha squared over 2 h bar squared. So if we will try to write this energy in terms of momentum, the given momentum p0, we can actually write this as negative p naught squared over 2m, where p sub 0 or p naught is m alpha over h bar. So this will be our starting point. So from here, we know that from our general definition of the momentum space wave function, it's summation of n cn psi n e to negative I et over h bar. So in this case, since there's just one wave function, so we no longer need to sum. So it will be just psi e to negative I et over h bar. That's just the wave function. There's only one psi n, psi 1 or psi 0 in this case. So psi 0. So basically this is psi 0 and E0. Okay. So what you will do is to construct your wave function where psi naught is this one, E naught is given by that one. And then use the Fourier transform to solve for the momentum space wave function. So this is just 1 over square root of 2 pi h bar integral of e to the negative I px over h bar. Yes. Okay, so you construct your position space wave function first. So this is now your position space wave function. Psi naught is this one. E naught here is given by that one. Then you integrate, use that one, multiply by this term here, then integrate. So that you can solve your momentum space wave function. I will just go through with the general solution because this will be a long solution. So you do that, you substitute that, and you will get, I will show you the final answer. Integrating that using these values here, or these expressions here, you will get a value of square root of 2 over pi p naught to the power of 3 halves. By the way, this integral is from negative infinity to positive infinity. P naught to the 3 halves e to the I p naught t over 2m h bar over p squared plus p naught squared. This will be your momentum space wave function. So you have transformed now your position space wave function to a momentum space wave function. But that's not the real problem here. You're asked to find the probability. So to find that probability, the probability asked in this problem, it's the probability that the momentum would be greater than this value. So that the momentum is actually the probability that the momentum is greater than p naught. So you need to get the absolute value squared of this one, dp, integrated over dp, and integrate it from the limits greater than p naught. So it's from p0 to infinity. So greater than p naught. So p0 to infinity. That's what greater than p naught means. And in this case, I will leave this to you. So you will need some integral formulas here. Similar with the evaluation of this momentum space wave function, you will need some integral formulas. This is just 1/4 minus 1 over 2 pi, or approximately 0.1 or 10%. 0.1 or 10%. So that's the probability that if a particle is trapped in a delta function well, and you made a measurement of momentum instead of position. So since you already know the position space wave function, you convert it via Fourier transform to the momentum space wave function and get the absolute value squared of that. Again, the probability only depends on the limit. You will still have the same formula, integral of the momentum, integral of the wave function squared. But what matters is the limits. So it's from A to B, then A to B. It's greater than P naught, then it's P0 to positive infinity, greater than P naught. In this case, you will get a probability of 10%. Okay. Let's have another example. So you are asked to show that in momentum space, the expectation value of position looks awfully familiar to the expectation value of momentum in position space. So if you will recall, the expectation value of P in position space is just integral of the position space wave function psi star, and then you have hbar over I, the operator form of momentum, partial with respect to x psi dx. The only difference, even though they are symmetric, hbar over I partial with respect to x dx here, this is hbar over I partial with respect to b. Sorry, this should be dp. So hbar over I partial with respect to b and integrated over p, except for the negative sign. Okay, so this further means that in momentum space, your operator form of position is negative hbar over I, say d dp. This is in momentum space, and in momentum space, the momentum operator p is just p, because that is the natural space or natural home of the momentum. But in position space, your p operator is this one, hbar over I ddx. So that one, we need to show that in momentum space, our position operator is no longer just multiplication by x, but it's now a first order derivative in momentum. Okay. So we will start by okay, we will start with our general form, the expectation value of x in position space, and that will give you psi star x psi star dx. Now we will use the Fourier transform formula for psi star, or sorry, psi rather, which is just 1 over square root of 2 pi h bar integral of e to the I negative ipx over h bar, sorry, positive ipx over h bar p dp. So we will use this Fourier transform formula. We will use this value for psi here. So basically, the psi's here are this integral here. So you do that. So I will just go through with the general solution because I can't present to you the whole very detailed solution. So that is what we will do. You substitute psi here with this value here. So basically this is an integral. This is also an integral. So essentially you will now have three integrals or two integrals inside the integral. So you will do some integration by parts. And when you encounter, again, we have encountered this in the previous lesson, when you encountered an integral like this, e to the I p minus p prime x over h bar dx, this is just 2 pi h bar conical delta of p minus p prime. So we have encountered this type of integral before. So that's just a Dirac delta, basically. The Fourier transform of the Dirac delta is the number, just a number 1 over 2 pi, actually. So basically, that's just the steps. You need integral. We will do some integration by parts here. And whenever you encounter this integral, that's just 2 pi h bar the Kronecker delta. And you will then achieve, by the way, in the substitution, since this will have an integral, this will be an integral in p. This p will be a p prime, so meaning its differential will be p prime, and the other one will be p and dp. That is where your p prime and dp, because we will now have two integrals of p here, so that we can differentiate which is which integral, which values of p belongs to which integral. Then we will set the one p here with p prime, and the other is just p. So when you substitute here, this here, take the conjugate, so negative I, and instead of p, use p prime here. So that's what you will do. Until you can get rid now of any x, and you will achieve this final form. So it's now in terms of phi star. You group all of your other terms in the middle, in the operator, and then that. By the way, there's something you will need here. For instance, you will actually need this one. This is actually a hint. X e to the ipx over h bar is basically h bar over I So if you see something like this, x e to the ipx over h bar, that's actually just the derivative of e to the ipx over h bar with respect to p multiplied by this constant h bar over I. That one. So if you notice derivative of this with respect to p, this e to the ipx over h bar, and then we're taking the derivative with respect to p, so the constant will be ix over h bar. So ix over h bar, you cross multiply this one. So you will need this formula or equation for this problem. Okay. So basically that's the end of this lesson. So we now have generalized the statistical interpretation of the wave function to not only mean position wave function. So depending on your physical quantity, whether it's position, momentum, or energy, you need to find the specific wave function for that in order to find the probability of finding position, momentum, or energy, or probability of finding that physical quantity Q in general. So in the next lesson, we will be generalizing the uncertainty principle. I will see you again in the next lesson.